Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Welcome back. We will continue our second part of the lecture. For the topic on gas turbine cycle for aircraft propulsion, we have already looked at the item 3.1, criteria of performance, and now we would like to go into the intake and propelling nozzle efficiencies. So basically the subtopic 3.2 is being divided into two parts. One is on the intake efficiencies and the second part is on the propelling nozzle efficiencies. At the end of this session, you should be able to explain the function of an intake, or known as inlet, compare the two types of efficiency for intake, and further explain the advantages of having convergent propelling nozzle, and finally propose the limitations of the design of a propelling nozzle. So there are 4 learning outcomes that you probably need to pay attention to. In terms of the intake and propelling nozzle, in general, the turbine just produces sufficient work to drive the compressor, and the remaining part of the expansion is carried out in the propelling nozzle. So simple turbojet engine as well as the ideal cycle as shown here. Okay, we have the TS diagram, right? Ideal TS diagram from station 1, 2, 3, and 4 and 5, and it is denoted by this schematic of the turbojet engine, where you have the intake or the inlet, we have the compressor, we have the combustion chamber, the turbine, as well as the nozzle. So those numbers from A till 5 is being denoted in the TS diagram, as such. Let us look into the intake. The intake has a significant effect on both the engine efficiency as well as the aircraft safety. You cannot just simply say that, oh, you can just use any type of intake for any type of engine. It has a specific design for specific purposes. And the main function basically to minimize the pressure loss up to the compressor phase. Basically, you want the intake or the inlet will prepare the air before it goes to the fan or the compressor phase, while ensuring that the flow enters the compressor with a uniform pressure as well as velocity at all flight conditions. So when you design an inlet or intake, you must ensure the correct angle, the correct length, as well as the area involved in order for you to get the correct pressure, velocity, and minimize the loss at the before it goes to the compressor stage. Non-uniform, what will happen when non-uniform or distorted flow? Okay, if you don't design it properly, or you use the wrong design for a different or for a typical type of engine, it may cause the compressor surge, which result in either engine flame out in the combustor or severe mechanical damage due to the blade vibration induced by unsteady aerodynamics effect. So this is the causes, the damage that going to be happen if you do not have a uniform or you have a distorted flow. And engines may be installed in the fuselage, in ports, such as in the wing or rear fuselage mounted, or buried in the wing root. You can see that so many other installation of the intakes for the engine. The design of the intake will involve a compromise between aerodynamic as well as the structural requirement. So as we have already gone through in the design process of the engine, so you will have a part on the aerodynamic as well as the part on the structural requirement that needs to be balanced in terms of the both the requirements, right? So this is just an example of the S-band as well as straight through intake. So this is the S-band. Okay, let me just find my pen there. So you did where the air will go into the S-shaped duct. In this case, it is straight going out through the duct. So in this particular case, there is a band where the design involve the intake, a compromise between the aerodynamics as well as the structural requirement. Okay. The current design of a compressor require the flow enter the first stage at an axial Mach number in the region of 0.4 to 0.5. So for a typical engine, you will have the speed or the axial Mach number to be in the range of 0.4 to 0.5. And for subsonic aircraft, will typically cruise at Mach 0.8 to 0.85, while supersonic aircraft may operate at speeds from Mach 2 to 2.5. So you need to be able to design a special intake at a higher speed. At takeoff, with zero forward speed, the engine will operate at the maximum power as well as the airflow. The intake must therefore satisfy a wide range of operating conditions. Okay, and the design of the intake also requires close collaboration between the aircraft designer and the engine designer. Right? To account for the effect of friction in the intake, we must first consider the intake as an adiabatic duct. Okay, what do we mean by adiabatic duct? Meaning that there's no heat as well as work transfer happening. Right? And then what happened? The stagnation temperature is constant and there will be a loss in stagnation pressure due to friction and due to shock waves at supersonic flight. Right, let us look at the condition under static conditions. What happened actually? The intake acts as a nozzle in which the air will accelerate from zero velocity, because you do not have at the beginning of the movement of the aircraft, right, that the incoming air is zero or low CA to C1, meaning that probably there are some velocity for the air before it goes into the compressor inlet. Okay, whereas for normal forward speed, we have the intake performs as a diffuser, right? The air going into like a duct, with the air decelerating from CA to C1, right? Where under static condition, air will accelerate from 0 to CA or from CA to C1. Whereas in normal forward speed, the air will decelerating from CA to C1 and the static pressure will rise from PA to P1. Okay, so the stagnation pressure at the compressor is of interest and which is referred to as the ram pressure rise. So at supersonic speed, it will comprise the pressure rise across a system of shock waves at the inlet followed by that due to subsonic diffusion in the remainder of the duct. So it is different at a supersonic speed. So there are shock wave form, okay, in the inlet before it goes to the downstream the engine. The intake efficiency can be expressed by the term zeta I, okay, intake efficiency, right? So we have zeta I here, and it is the isentropic efficiency, which is defined in terms of the temperature rises, and the ram efficiency zeta R, which is defined in terms of the pressure rises. Okay. From figure 3.7, okay, we have the intake loss over here, okay, And it is the TS diagram where we have the expression for TO1, okay, and the pressure ratio at PO1 and PA, because we are dealing at the intake section. So from ambient to section 1, which is at the compressor stage, where T prime 01 is the temperature which would have been reached after an isentropic ram compression to P naught, right? And T prime 01 can be related to T01 by introducing an isentropic efficiency or zeta I. It is defined by equation 3.9 here, and it follows that, right? This expression, okay, where the difference between T prime 01 minus the ambient temperature is equal to this expression, so that zeta I, the isentropic efficiency, can be regarded as the fraction of the inlet dynamic temperature, which is made available for the isentropic compression in the intake, right? And looking at expression 310A, the intake pressure ratio can be found from here, and remembering that the Mach number, okay, is equal to the speed of the aircraft divided by this gamma RT to the power of half, and this expression we have gamma R equal to this expression, and this equation can be written as 310B as such. Okay, this normally being given in any examination question, we will provide this particular ratio. The stagnation temperature can also be expressed in equation 311 in terms of the Mach number. So the ram efficiency is now defined by the ratio of the ram pressurized to the inlet dynamic head, namely as the following expression. Okay. Looking at the intake efficiency, it will depend upon the location of the engine in the aircraft. Okay, whether it is at the wing or at the port, or you have put it at the fuselage. Normally, a value of isentropic efficiency as 0.93 is used for subsonic aircraft. And the value will be less for supersonic intake. So imagine you have a supersonic intake, probably it is 0.8 or 0.7. It is getting less and less. In practice, neither the isentropic efficiency nor the ram efficiency is used for supersonic intake, because it is getting lesser and lesser. And it is more usual to quote values of the stagnation pressure ratio of P01 over PA as a function of the Mach number. So for subsonic aircraft, we normally use a typical value of 0.93 in terms of the efficiency of the isentropic. And then for supersonic intake, we normally do not use it. We just use the stagnation pressure ratio as a function of the Mach number. Knowing the pressure recovery factor, okay, the pressure ratio can be found from this expression where POA over PA is given in terms of the Mach number by the isentropic relationship as follows. So we have this PO A over PA has already been given in terms of the Mach number by the isentropic relationship. And for the pressure recovery factor relating to the shock system itself, P0A over POA in terms of the shock is being given by this correlation, which is valid only for Mach number 1 to 5. Right? To obtain the overall pressure recovery factor, the pressure ratio PO1 over POA shock must be applied by the pressure recovery factor for the subsonic part of the intake, right? That is the first part of the lecture for this session. We have looked into the intake, where we have already defined the isentropic efficiency, at the same time the ram efficiency associated to the intake section or intake compartment. Now we look into the propelling nozzle efficiencies. It is a little bit long. In terms of the propelling nozzle, which is referred to the component in which the working fluid is expanded to give a high velocity jet. Remember, the expansion in the turbine is not fully expanded, right? And then that's where we need a propelling nozzle to give an extra thrust. So between the turbine exit and the propelling nozzle, there will be a jet pipe of a length. Okay, depend on the aircraft as well as depend on the location of the engine in the aircraft. Okay, so in the transition from the turbine annulus to the circular jet pipe, some increase in area is provided. So you have the AJ, so is provided. Basically, you have this one is basically the AJ to reduce the velocity and hence friction loss in the jet pipe. Okay, so when boosting or thrust boosting is required, like in the case of the afterburner, you may incorporate the afterburner section in the jet pipe section. So imagine this is the turbine, okay, where we have the hot air coming from the turbine stages, right? So we have the hot air going to there, and it is being slowed down. Okay, it is being slowed down in the diffuser, right? Okay, and then it is further accelerated in the jet pipe, basically right after the afterburner, because you have this diffuser basically to allow the combustion to take place here at the fuel that being injected at the jet pipe, and this then resulted in a much higher velocity to produce the thrust for the aircraft. The afterburning in a jet engine is sometimes referred to as reheating because you are putting more energy to the system, although it is not equivalent to the reheating between turbine that being used in the industrial gas turbine. Right? So the question arises whether a simple convergent nozzle is adequate or you need a convergent divergent nozzle in the system. So we must remember that higher thrust is required, not the maximum jet velocity. So this is quite crucial in our design. We want to have, some people say that, oh, we want to have a higher jet velocity, but actually the ultimate aim is to produce a higher thrust. For an isentropic expansion, the thrust produced is maximum when complete expansion, right? So the PJ is fully expanded to PA, which is occurs in the nozzle, right? The pressure thrust A5 times the difference between P5 at the nozzle exit minus the ambient pressure, and arising from incomplete expansion does not entirely compensate for the loss of momentum thrust due to a smaller jet velocity. Okay, but this is no longer true when friction is taken into account because the theoretical jet velocity is not achieved. And that the use of a convergent divergent nozzle would probably result in a significant increase in weight, right? Of course, you have more section over there. It also increase in length, it also increase in diameter, right? Obviously, it will also increase in major installation difficulties and finally penalty to the aircraft weight, right? And at operating pressure ratio less than the design value, a convergent divergent nozzle fixed proportion would certainly be less efficient because of loss incurred by the formation of shock wave in the divergent portion. So because it's happening at high speed, shock wave will occur in the divergent portion. So for this reason, aircraft gas turbine normally employs only convergent propelling nozzle. Compared to the rocket, maybe you have a different design where you may require a convergent divergent nozzle. The advantages of a convergent propelling nozzle, number one is basically you in terms of the variable area, so which is essential when afterburner is incorporated. Okay, convergent propelling nozzle. And then a thrust reverser, it is to reduce the length of runway required for landing. So you may have seen when typical aircraft landing, they have a thrust reverser being activated to get the aircraft to be stopped at a shorter runway. And then noise suppression. By having a convergent propelling nozzle, most of the jet noise is due to the mixing of the high velocity hot stream with the cold atmosphere, and the intensity decreases as the jet velocity reduces. So you have a lower jet velocity, you will have a lower noise generated. Figure 3.9 here showing a variable area, thrust reversal and noise suppression. So it illustrates the iris and central plug methods of achieving variation of propelling nozzle area. So you can have a typical shape like this, or you have having like a cone over there, or you may have a variable composition where we have a clamp shaft for reversal and also noise suppressor. So you have a bleed flow of cold air mixing with the hot air. So the noise level can be reduced by accelerating the mixing process. Right? By accelerating the mixing process, you will then definitely get a reduced noise, and this is normally achieved by increasing the surface area of the jet stream. At high supersonic speed, the large ram pressure, large ram pressure rise in the intake will result in a very high nozzle pressure ratio. Right? So the value of PO4 over PA, is then many times larger than the critical pressure ratio and may be as high as 10 to 20. This is quite high for the flight Mach number in the range of 2 to 3. Right? And variable exit or throat area is essential. So you want to have to control the exit area. So you may want to be able to adjust the diameter. It is to avoid shock losses over as much of the operating range as possible. Okay, and the additional mechanical complexity must be accepted. So you must put additional mechanism to control the movement of the wall associated with the nozzle. So in terms of the limitation of the design, of course, the exit diameter must be within the overall diameter of the engine. You do not want the propelling nozzle to be bigger than the diameter of the engine itself. Otherwise, the additional thrust is offset by the increased external drag. It's quite weird. You want to increase something, but you're being penalized by having an extra external drag. And in spite of the weight penalty, the included angle of divergence must be kept below 30 degrees, right? Because the loss associated with divergence or non-axiality of the jet increases sharply at greater angle. If you have more than 30 degrees, let's say 45 degrees, 60 degrees, has already been proven that you have a higher losses, right? Two methods are commonly used for propelling nozzle loss in cycle calculation. The first one is isentropic efficiency, right? And then we have the specific thrust coefficient. We use the symbol K, F. F for thrust, K is specific coefficient for the thrust, and defined as the ratio of the actual specific gross thrust, as denoted as this expression. Figure 310, nozzle loss for unchoked and choked flows. I believe you already have a little bit background in terms of the what is a choke conditions or unchoked condition for the nozzle. in your propulsion subject. So the real isentropic processes on the TS diagram is shown here, and the isentropic efficiency is defined by this expression. Okay, for the jet, that's why we have TO4 and T5 involved. This is also the temperature equivalent to the jet velocity, because we know that the temperature at exit nozzle equal to the temperature at the inlet of the nozzle area. Okay, for pressure ratio up to critical value of P5, right, will be equal to PA in equation 312, and the pressure thrust is considered 0. And above this critical pressure ratio, the nozzle is choked. Okay, but P5 remains P critical, and C5 will remain sonic, right? And the critical pressure ratio PO4 over PC is the pressure ratio PO4 over PO5 itself, and it yields that M, or the Mach number at station 5, will be equal to 1. Consider the corresponding critical temperature ratio of TO4 over T critical. It is the same for both isentropic as well as the irreversible adiabatic flow. And this flows from the fact that TO5 equal to TO4 in all cases of adiabatic flow, because there's no heat transfer, and thus we can write TO4 ratio over T5, which is equal to TO5 over T5, with this expression in terms of the Mach number at station 5. Okay, and putting M5 to be equal to 1, you will get the ratio of TO4 over critical temperature, which is as the specific ratio, heat ratio, gamma plus 1 over 2. Having found the critical temperature from equation 313, from figure 310b, the value of the zeta J, the propulsive efficiency, which yields as C prime C, which is the temperature reached after an isentropic expansion to the critical pressure, which is PC. Namely this, we include the expression of the propulsive efficiency there for the jet. And PC is then given by this expression, where we have the term zeta J inside, with the ratio of critical temperature over TO4. And substituting TC over TO4, we have the critical pressure ratio now, right? And the remaining quantity necessary for evaluating the pressure thrust is the nozzle area, A5. That's why I said A5 nozzle area for the jet pipe is crucial. And with density at the critical is obtained from the ideal gas temperature equation, right? PC over RT, and we have the critical velocity from this expression. That would conclude our session. So basically, later when we have example, you will be using the, let's say you are being asked to calculate the efficiency, isentropic efficiency for atypical inlet design, or RAM efficiency for the intake. At the same time, you are probably going to be calculating the efficiency for the jet associated with the nozzle. So with these formulas that been given, normally we will provide the equation in the examination, so that you can easily use it to obtain the appropriate efficiency associated with the intake as well as the propelling nozzle. So with that, we will continue the simple turbojet cycle, turbofan engine, turboprop engine, and thrust augmentation in our following lecture.